Okay, hi. So in this central exercise, we need to find the radius and the angle for a bounded Keplerian motion. And since this is a long and very, very tedious exercise, I'm just going to comment on what I've done before. So after setting up the energy equation and substituting by inserting the equation for the preservation of angular momentum, we get a equation that we're gonna solve for r dot squared. And before we're going to solve it by separation of variables, because there's a differential equation, we're just gonna manipulate the terms a little such that we can insert the eccentricity and the major axis, so parameters that we know well, inside there, so we can work easier with them. Right, so we're doing the we're gonna combine terms, and when we have done that, we get a equation, right? And right now we're gonna determine what the measure axis is of the ellipse. So the measure axis of the ellipse is just the diameter, or the large diameter of the ellipse divided by half, and r0 and r1 are the moments where r dot is 0, because those are the extremas. So when we're solving for the radius where r dot is 0, we get a quadratic equation that we're going to solve. Solving this, well, gets us two solutions, of course, because there's the smaller and the larger one. And when we insert that for our major axis, well, the discriminant, so the root sign cancels out. And doing this, we get minus gamma divided by 2e. And this is nice because then we can insert this for a. And now for the eccentricity, it's defined by the ratio of, well, the distance from the center to the focus point, like at the origin, divided by the major axis. So it's the ratio of them. And performing the calculation and inserting what we know from a and r0, because r0 is the is one of the solutions. We once again get a term, right, that looks kind of nice, and sums up pretty nicely. And when we square that and multiply that by a squared, we get what we have as another term inside the large bracket. Yeah, so just performing the calculations, and you observe that this term is present there. And now we can just resubstitute everything in, because afterwards we're going to parameterize, we express the parameterization in terms of a and epsilon, right? And now we can go on to solve the differential equation. And doing just some algebraic manipulation, right? And for solving that, we're gonna add a, or subtract an a and add an a, and divide that integral into two integrals that we can solve more easily. And we observe that for the first one, well, it just is square root of that, because if you're substituting, for example, minus r minus a squared, then our derivative, the differential, is just what stays in the denominator. And for the second one, it's just the inverse sign That's something that we've done in the homeworks many times before. Yeah, so I'm gonna skip over that. But the problem is, well, it's an ugly expression, and we cannot solve explicitly for r and t. And therefore, what we're gonna do is parameterize the differential, the integrals in such a way that we get a nicer relationship between t and r. So we're going to substitute for r a times 1 minus epsilon cosine of xc. And doing that, well, we'll get a result that looks better. So we're just right now inserting the substitution in. R minus, yeah, r minus a, then just minus a epsilon cosine c squared. And then we can observe that this is a simple expression, so a squared epsilon squared sine squared, and therefore this cancels out with the a epsilon sine xc in the denominator, and therefore the integral becomes pretty nice. Because that's one linear term and one cosine xc that we have to integrate, and this is pretty easy. Some constant term. And now we're gonna think what is t of 0. And well, t of 0, if we put in insert c equals 0, so we have just a times 1 minus epsilon. And well, a minus a times epsilon, since epsilon is a minus r0, is just r0, and therefore t of 0 is the starting point, or like the point where the planet is at the closest point to the another massive object. So we could easily safely say that this is when the time is 0 also. All right, and now we can simplify the term. Because a is negative gamma divided by 2e, we can substitute the e inside this expression and get a cubed m divided by gamma times xc minus epsilon sine of xc. Right, awesome. And once we have done that, we have parameterization of t and r. It's not explicit, but it is explanatory of the relationship of these two. Right. And now just to be checking, well, t is a time, so it has to be monotonically increasing. And when we check that by differentiating with respect to xc, we have the factor in front of it, 1 minus epsilon cosine of xc. And since cosine of xc is less than 1 and epsilon is less than 1, dt by dxc is indeed larger than 0. And therefore t is monotonically increasing. And now we're going to solve for our angle. Right again, we substituted for the angular preservation of angular momentum. We do the neat little trick that we have dphi by dt is dphi by dxc divided by dt by dxc. And we can now substitute everything in that we know already, because dt by dxc is, we have calculated that. And r we have also calculated already. So we're just going to insert that back inside the equation. And we're going to solve for the phi by dxc. Simplifying a little. And we're going to get a differential equation that we have to solve. And an integral to compute that is not that easy. Because phi is then, well, the root of this of dxc over 1 minus epsilon cosine of xc. And for solving that, we look at the cosine xc in the denominator, and well, we know from the double angle formula that cosine of 2xc is like this, and therefore cosine of xc will be cosine squared of xc halves minus sine squared of xc halves. So we can substitute this into the equation, and we can use the trig identity is that 1 equals to cosine xc squared plus sine squared of xc halves. And once we have done that, we can combine the terms like this and pull 1 minus epsilon cosine squared of xc halves out. And you're going to see why. Because once we have done that, it's appealing that we substitute the expression there with u, because then our du is very similar to what we have already there in the denominator. So we have cosine squared of xc half when we differentiate tangent of xc halves. So performing the substitution then yields us an integral expression that can be integrated easily. So substituting dxc and u and all that stuff gets us, after eliminating the common terms top and bottom, right, integral of du by 1 plus u squared. And this is just tangent, the inverse tangent of the argument. The argument has been u, and writing again the factors in front of it, arctang of what you have substituted there, pretty complicated looking equation, and that is for determining phi. Alright, and phi of 0 is at the starting point, so it's once again 0, and we don't need a constant as integration constant. And now we're going to look at the factor of the arctang, because when we substitute for epsilon what we know, it's an expression that will simplify it greatly. So epsilon we have computed 1 plus this term right there, plugging that inside, subtracting a1, yields us an expression where many terms will cancel out, for example the L, the M, one of the gamma. So the L is a mistake here, yeah, it's 1. And 2e divided by gamma is exactly 1 over a, the inverse of a, and therefore this entire expression is just 1. And because we have the 2 up front there, phi of xc is 2 times arctang, the inverse tangent. So it's still ugly, but it's not as ugly as before. Okay. So now we're going to verify that this parametrization really yields us an ellipse. So we use that parametrization that we have performed before, and going to substitute back in what we know, everything. Right? So we use the same trick of cosine. So use the reduction formula for the angle. Then we use one trig identity to substitute 1 plus tangent squared of xc halves. Because tangent squared of xc halves, well, using the phi of xc that we have calculated before, we can substitute this back in. So it's a lengthy expression, but we can further simplify. This tangent, we can now use once again the trig identity Then resubstituting our double angle formula. So it is very algebraic, so like it's very tedious computation. Yep. And then we're gonna try to simplify. Subtracting 1 gets us this expression there, and then multiplying top and bottom with 1 plus epsilon times 1 plus cosine phi. Yeah. So multiplying top and bottom with that factor will further simplify things for us. And this point is just calculation and being careful not to drop anything. And now we're gonna multiply it through. Many things cancel, and we're just ending up with 2 plus 2 epsilon cosine phi. The 2 get cancelled out. And once again, we can subtract the 1 in a way that things get simplified. Multiplying through, the 1 vanishes, the cosine phi times epsilon vanishes, and we have epsilon plus cosine phi. This entire expression there. And last time that we used the trick with adding or subtracting 1 and simplifying things and crossing things out, we arrive finally at the expression that is indeed like an ellipse. Awesome. Okay, and yeah, so now we have, so now we're gonna move on to finding out R if the energy is 0. So when we're dealing with a parabola. And in this case, well, R of phi just gets reduced to P over 1 plus cosine phi. And we're gonna find out what R of t is. Because we have calculated it for bound Keplerbewegungen motion. If it's unbound, then the energy is larger than 0, then you just have to do some manipulation which are not that different, so I'm not going to cover it here. And now, because the constant E is just 0, the calculations are very much simpler. And solving for t, it's just like solving another differential equation, multiplying top and bottom by r. We get this expression inside the integral. And you're going to multiply through by m. And therefore we have to solve this integral here. And for doing that, we're going to manipulate it once more, such that we can integrate it more easily. So we're going to multiply top and bottom by 1 over 2 gamma, and 2 gamma, such that we can add and subtract an L squared, because then we have, once again, 2 integrals, where both of them are easier to integrate than the overall integral. Because now observe that one of them gets reduced to a normal square root and not 1 over a square root, and the other one is just also pretty easy to integrate. And once we have that, it becomes evident what we have to integrate. And these are elementary integrals. Just be careful with the factors. And then it's just about summing up and putting terms together. So because the first term is 2 gamma mr minus L squared raised to the 3/2, we can pull the square root out of it and combine it with the second term, where there also is the same square root expression. And when we have done that, we can combine the terms together because they have a common factor. Once we have the denominator matched, we can add them together, and then we'll see that the entire term is not that ugly anymore. And remember, this is t, and therefore we have found an implicit formula, and also the constant we will set it to 0 because at the time where r is minimal, it's the point where the square root vanishes, and that's the point where the object is closest to the another object. And that's at p divided by 2. And now we have found the implicit formula that we can solve.